Welcome back, Physical Science 20. This is the PW 1.3 section, Mechanical Waves, Interference and Diffraction. So in PW 1.1, we looked at just wave properties. 1.2, we looked at wave speed. So now we're going to look at these two concepts. So illustrate constructive and destructive interference in one and two dimensional waves, including the principle of superposition. And the standing waves part we're going to do in the reflection unit. So that's going to be actually in the next unit after this. And using point source and straight source waves. Observe and describe diffraction of waves through single and double slits. So we'll be looking at that. There'll be a couple of online simulations I'll be using to show that as well. So superposition of waves. Suppose a pulse traveling down a spring meets a reflected pulse coming back. In this case, two waves exist in the same place in the medium at the same time. Each wave affects the medium independently. So that's a key thing. The principle of superposition states that the displacement of the medium caused by two or more waves is the sum of what each wave does individually. Okay? So if you look at this little diagram over here, if we have a pulse going this way and a pulse going this way, they meet each other. To figure out what happens when they meet, you just simply add them up. And the key thing here is to think of this as like the equilibrium position of let's say this is a slinky spring or a rope. It's at 0, okay? Now anything kind of above it we could say is in the positive position. Anything below is in the negative position. So if this had been like, let's say, +3 units, and if this is -3 units, of course, +3 minus 3 is going to be 0. So right when the top part of this at +3 is in the same spot as -3, right here, of course, it is 0. And then as you see, this pulse then just keeps moving as if nothing happened. So they act individually, and then they continue through as if nothing happened. Okay, so they combine to make a new wave. It could be a cancellation of a wave, or as you look at the diagrams down here, if we had the same thing, if this crest is +3 and if this crest is +3, when they meet in the middle, the +3 and the +3 make a big +6. So we could have a larger wave or pulse being made, or a smaller one, or a complete cancellation as you see in this one. So the result of the superposition, the positioning of the two waves, is called interference, because that's what's happening here. These waves are interfering with each other. Wave interference can be either constructive or destructive. When the two pulses meet with equal but opposite amplitudes, the displacement of the medium at each point in the overlap is reduced. So we can think of the constructive part, doing something constructive. The overall wave is going to be larger than it was before, such as in this case down here. +3 gives us +6. Destructive, the resulting wave will be smaller. So you could have waves on opposite sides of the equilibrium or rest position, making a wave that is smaller. The superposition of waves with equal but opposite amplitudes causes destructive interference, as shown over here. When the pulses meet or in the same location, the displacement is 0, and point 2 is called a node. So that is where a complete cancellation occurs. Complete cancellation. Constructive interference, again, doing something constructively, making it bigger, occurs when the displacements are in the same direction or in the same phase. The result is a wave that has an amplitude greater than the individual ones. And of course, this diagram on the right shows constructive interference, making a larger pulse. A larger pulse appears at point A when the two waves meet. Point A has the largest displacement. That is called an antinode. If a node is complete cancellation, an antinode, the prefix anti implies the opposite. So we could say largest position. Okay? Two pulses pass through each other without changing the shape. So they meet, they either make destructive interference or constructive interference, and then they keep moving as if nothing happened. And again, on the next page here, the resulting the pulse with overlap is the sum of the two pulses as shown over there. So what we'll do is run through an example dealing with this. We have two waveforms here. Let's say they're kind of funky shapes. One's kind of a rectangular shape and one's a triangle shape, and they're coming towards each other. What happens right when they meet? Like when the middle of this pulse is over top of the middle of this pulse, and then immediately after. So what I'm going to do here, we can see that this rectangle is 2 squares above, this triangle is 2 squares below. So what I'm going to try to do is draw it down here. Now, if you make a little dot right here, this will represent the equilibrium position. Okay, the point in which if this had just been a string without any movement, it would just be a flat line right there. So that's going to be our 0 area. Anything in this direction we'll think of as being the positive direction, and anything below that equilibrium position is the negative. So if I just use a pencil here, this is the equilibrium position. That is if it was not even moving. All right, so now if I look at the question at hand here, this rectangle is kind of like a 4 square by 2 square. So I'm going to, towards the middle, just draw it. So let's make it right here. I'll draw, maybe I'll use a pencil for this. So let's draw it here, 4 squares by 2 squares up. Okay, so if that is all I had, that's what it would look like. Now, I want to look at when it interferes exactly with the middle of the other pulse. So this pulse, of course, is going to move, and eventually they'll be over top of each other. Now this is down 2, also 2 by 4, except it goes up angled here. So it looks something like that. So down 2, over 4, over 4. Oh, I went over 3 in both of these. Darn it. I'll have to redraw that. Because it should be 2 by 4. There we go. And then 2 by 4, so it's going to be something like that. It doesn't have to be exact. Good. So now what I'm going to do is apply the principle of superposition by looking at what's happening at each area. Now the best way to do this is to look at where each vertical line is here on the graph and compare the 2 points of the 2 pulses. So if I look here, let's use my pencil here. So on this first line, this one is at +2, this one is at -2. So of course, +2 minus 2 is 0. So I'm going to make a little dot right there. If I continue on over here, I have plus, and maybe what I'll do is I'll do this at each point here just to show this. You wouldn't have to show this, of course, but just for this video I'll show it. So +2, -2. All of these, on all of these vertical lines, this pulse is going to have a point at +2, +2, +2. Over here, I can maybe say this is, I don't know, negative 1.6, negative, let's see, 1 and a bit, negative 1.2. It's a little bit less than -1, so maybe to negative 0.8. And here, of course, it's 0. So if I look over here at this far one, again, I'm just looking at the vertical line. +2 plus 0 is +2. So that's easy to do. Let's look at this one. So if I'm looking over here, this point at +2 combined with the point at negative 0.6, if I do the math there, +2 minus 1.6 is going to give me +0.4, so a little bit less than halfway. Over here, +2 minus 1.2 is going to give me +0.8. So +0.8 is what happens when those interfere. Then over here, +1.2 minus 0.8, 2 minus 0.8, that's 1.2. So you can see the pattern there. What will happen is that the waves will come. So we can just simply say at that point here, this is the result. Then of course, it'll shoot back down to here and then be 0 there and 0 there. So that is the interference that happens right when they overlap. Right when they overlap. A few moments after overlapping, So of course this rectangle, so they combine to make the orange shape that you see here. And then after they pass through each other, that rectangle will keep moving as if nothing has happened. So it was moving from left to right, so it's over there. And that little triangle that I had, 1, 2, 3, 4, down 4. So it'll keep moving as if nothing happened there as well. All right, so that's how interference works. They're constructive, destructive. So over here, of course, this would be a case of destructive because I don't have anything bigger than +2 or anything more negative than -2. Because the amplitudes are on opposite sides, the overall wave is less than each one of these individually. So that would be destructive interference. All right, I think what we'll do is we'll stop the video there and we'll come back and do part 2 in a bit.